Okay, so we're going to look at this problem, and here they want us to determine the potential difference VAB. So where is VA? So VA is here, VB is here. So this is what we have to determine. And looking at the way the arrowhead is being presented there, it's like here they're kind of trying to say that B is at a higher potential. So treat B to be positive and A to be negative. So if it turns out that A is actually at the higher potential and B is at a lower potential, then this is going to be negative. The voltage VAB will be negative. But if VB is at a higher potential than A, as in B, if B is at a higher potential than A, then it's going to be positive again. If A turns out to be at a higher potential than B, then our answer for VAB will be negative. But if B turns out to be at a higher potential than A, then our answer is going to be negative, to be positive in that case. So I'm interpreting that based on the way the arrowhead there is being presented. If the arrowhead was not there, I would have used VAB to mean they're saying positive is at A, B will be negative, and I would have interpreted to say, had they used VBA, then positive will be at B, and like that. But the arrowhead there will mean that I'll take it as B being positive and A being negative. With that out of the way, how do we find the potential at A and the potential at B? So our VAB, based on the arrowhead again, I'll take it as the potential at the positive end. Positive end, we're taking it to be at B, minus the potential at A. So this is what we're going to use to find what they want us to do. So what is the potential at A and what is the potential at B? Okay, so there are a number of ways that you can actually work out this problem. You can use nodal analysis, you can use Kirchhoff's laws, or you can just go with the plain old basic method of just circuit analysis. For this is not very clear where positive and negative is, but let's take it that positive is up here and negative is down here. So in the approach that we're going to use here, so what we're going to do here is we're just going to reduce the circuit so that it becomes a little bit easy. Our target is just to find the voltage at this node and the voltage at that node. So how do we do that? To reduce the circuit, we observe that a few things can be combined. For example, these two resistors are parallel to each other. So the 16 ohms and the 16 ohms are in parallel. Combining those two, what are we going to get? So when you combine these two, we see that we're just going to get 8 ohms. So meaning our circuit can be redrawn by combining those two resistors, so that now we can present these two as just a combination of both. And now our circuit will look like this. And this will be an 8 ohm resistor. After that is done, we also see that these two are also in parallel, and their parallel combination gets to join at the node A. So those are in parallel. So with that in mind, we can actually combine them. And for those, we have it's 10 by 15 over 10 plus 15. So this will be 150 divided by 25. So here we get 6 ohms. So we now see that these two can be combined, and in place of those, we just end up with a 6 ohm resistor. Okay, now we have simplified our circuit a little bit. Next up, you see, all we want is the voltage VA and the voltage VB. So how do we get those? You see, because these two lines are both in parallel, as in this is connected in parallel to this. So each one of these sides will see the same voltage because they are both connected to the 12-volt supply. So each one will see 12 volts. But how much will they use? You see, if the 12 volts is what is being fed to this line, the 6 ohm resistor here will use part of it. The rest will go to the next one. Now for this one, because this is 6 ohms, this is also 6 ohms, it means that they'll use the same, implying that the 6 ohms on top will use 6 volts. 6 volts will be dropped here, and the remaining 6 volts will be dropped by that. So in other words, if 6 was lost here, what remained of the 12 must be 6. That's what passed through this point and then went to be lost by that 6 ohms at the bottom. We could have also used voltage division. Since along this line, this is connected parallel to a 12-volt supply, VA, the voltage at A, is basically the voltage that goes towards that last resistor. So to find the voltage that goes toward this resistor by voltage division, it's that same resistor, 6 ohms, divided by the sum of the two resistors in series, which is 6 and 6, multiplying the voltage they were sharing. We see that this will be 6 over 12 multiplying 12. We see that the voltage that goes down there will have to be 6 volts. So VA comes out as 6 volts. Now how about this side? This side again, want to find VB, which is here. Remember, in the same way, this is connected parallel to the voltage source, so meaning even here, the voltage that comes to this branch is going to be 12 volts. But the two resistors, the 4 ohms will use, what will remain, that's what will pass through B, going towards 8 ohms. So the voltage VB we are looking for is the voltage that will go towards the 8 ohm resistor. So if we can find the voltage that will be dropped by the 8 ohm resistor, that will actually be our VB. So we'll use voltage division again. So how do we use voltage division? It is that resistor, which is the 8 ohms, divided by the two resistors in series, multiplying the voltage they were sharing. These were sharing 12 volts. So from here, we have 8 divided by, when we add these, we have 12. Then multiplying this. So yes, that's 12. So the 12 here and the 12 there will cancel out. And then the 8 is what will remain, because the ohms cancelled. So the answer is going to be 8 volts. So VB is actually at 8 volts. Now to find VAB, and remember, according to the arrow head there, according to this arrow, we interpreted that positive is at B, negative is at A. So meaning we're going to say VB minus VA. VB, 8 volts. VA, we found 6 volts. When we do the math here, we find that VAB turns out to be 2 volts. So this is how we answer this problem.